Welcome, fellow explorers of the cosmos, to a journey through the most frigid realms of our universe. Tonight, we'll travel together to places so cold that they challenge our very understanding of temperature, matter, and the fundamental nature of reality itself. As we embark on this peaceful voyage through cosmic winter, let yourself settle into complete comfort, knowing that while we explore the coldest reaches of space, you remain warm and safe in your own cozy corner of the universe. Before we begin this chilling adventure, I'm curious, where are you listening from tonight? Are you bundled up in blankets in Minnesota? Perhaps with snow falling gently outside your window? Maybe you're in sunny California, enjoying the contrast between your warm climate and the cosmic cold we're about to explore? Or are you somewhere across the globe in London, Tokyo, or Sydney? And what time is it where you are? Is it your usual bedtime? Or are you a night owl seeking solace in the universe's most serene extremes? Close your eyes now and imagine yourself wrapped in the warmest, most comfortable blanket imaginable. Not just any blanket, but one woven from starlight itself, protecting you from the infinite cold of space while allowing you to safely observe the most beautiful and frigid phenomena in the cosmos. Chapter 1: Understanding Cosmic Cold, the Language of Absolute Zero. To truly appreciate the coldest places in the universe, we must first understand what cold really means. Temperature, at its most fundamental level, is simply the measure of how fast atoms and molecules are moving. The faster they vibrate and dance, the hotter something becomes. The slower they move, the colder it gets. And at the theoretical limit called absolute zero, all atomic motion would cease entirely. Absolute zero sits at minus 273.15 degrees Celsius, or minus 459.67 degrees Fahrenheit, or 0 Kelvin on the scientific temperature scale. It's a temperature so cold that it can never actually be reached, only approached asymptotically, like trying to catch your own shadow. At absolute zero, atoms would be frozen in perfect stillness, locked in crystalline arrangements with no thermal energy whatsoever. Picture yourself floating in the depths of space, far from any star, far from any source of heat. Here, surrounded by the vast emptiness between galaxies, you begin to understand what cosmic cold truly means. It's not the cold of a winter day on Earth, not the cold of an ice cube or even liquid nitrogen. It's a cold so profound, so complete, that it represents the universe's natural state of rest. Gentle pause. The fascinating thing about the coldest places in the universe is that they often exist right alongside some of the hottest phenomena we know. Black holes, for instance, can have accretion disks that glow at millions of degrees, while their event horizons exist at temperatures barely above absolute zero. The universe is a tapestry of temperature extremes, woven together in the most beautiful and unexpected ways. As we journey through these frozen realms tonight, let yourself imagine the profound peace that comes with such stillness. In the coldest places in the universe, there is no frantic motion, no chaotic energy, only the serene, crystalline order that emerges when heat disappears and matter finds its most stable, most restful state. Think of this as we begin our journey. You too are finding your most restful state, settling into the peaceful stillness that comes as your body temperature naturally drops during the transition to sleep. You're experiencing your own gentle version of cosmic cooling, preparing for the deep rest that awaits. Chapter 2: The Cosmic Microwave Background, the Universe's Gentle Afterglow. Our first destination is perhaps the most pervasive cold in the universe, the cosmic microwave background radiation, or CMB. This is the afterglow of the Big Bang itself, stretched and cooled by 13.8 billion years of cosmic expansion until it now permeates every cubic centimeter of space at a temperature of just 2.7 Kelvin above absolute zero. Imagine the universe as a vast oven that was once incredibly hot, hotter than the core of any star, hotter than any fusion reaction we can create on Earth. In the first moments after the Big Bang, the entire cosmos was a seething plasma of fundamental particles, so energetic that atoms couldn't even form. The temperature was trillions upon trillions of degrees. But then came the expansion. As space itself stretched, carrying galaxies away from each other, that primordial heat spread out across an ever larger volume. Like breath on a cold morning dissipating into the air, the cosmic fire gradually cooled, its energy diluted by the growing immensity of space. For 380,000 years, the universe remained too hot for atoms to hold together. Electrons and protons existed as separate particles in a cosmic soup so dense and energetic that light couldn't travel far before being absorbed and re-emitted. The universe was opaque, like trying to see through a thick fog made of pure energy. But then, at that magical moment 380,000 years after the Big Bang, the temperature dropped just enough for electrons and protons to combine into hydrogen atoms. Suddenly, the cosmic fog cleared. Light could travel freely for the first time, and the universe became transparent. This first light, the cosmic microwave background, has been traveling through space ever since, gradually cooling as the universe expands. Pause to let this settle in. Where are you listening from tonight? Has the evening grown quieter around you as we've been talking? Take a moment to notice the temperature of your environment, the warmth of your bed, the cool air on your face. You're experiencing temperatures that are blazingly hot compared to the CMB, yet feel perfectly comfortable to your human senses. Today, we can detect this ancient light with sensitive radio telescopes. It appears to come from every direction in space, a gentle whisper of radiation that tells the story of our cosmic origins. At 2.7 Kelvin, it's nearly 300 degrees below the freezing point of water, yet it represents one of the most important discoveries in cosmology. The beautiful thing about the CMB is its incredible uniformity. Across the entire sky, its temperature varies by only tiny fractions, just a few millionths of a degree. This tells us that the early universe was remarkably smooth and homogeneous, with only the slightest variations that would eventually grow into the galaxies and galaxy clusters we see today. But within this overall smoothness lie subtle patterns, like ripples on an almost perfectly still pond. These tiny temperature fluctuations are the fossilized imprints of quantum fluctuations from the earliest moments of cosmic inflation. They're the seeds from which all the large-scale structure of the universe would eventually grow. When you look at detailed maps of the CMB, you're seeing the universe as it was when it was only 380,000 years old, a baby universe taking its first clear breath. The patterns in this ancient light are like cosmic DNA, encoding the information that would determine the future evolution of everything we see around us. As you drift towards sleep tonight, imagine yourself surrounded by this gentle cosmic afterglow. The CMB is everywhere, passing through your body, through the walls of your home, through the earth itself. You're bathed in the light of creation, cooled by billions of years of cosmic expansion into the most serene radiation imaginable. Chapter 3. The Boomerang Nebula, the coldest natural place we know. Now let's travel to a specific location, the Boomerang Nebula, located about 5,000 light-years away in the constellation Centaurus. This remarkable object holds the distinction of being the coldest natural place we've ever discovered in the universe, with a temperature of approximately 1 Kelvin, just 1 degree above absolute zero. The Boomerang Nebula is what astronomers call a protoplanetary nebula, though that name is somewhat misleading. It has nothing to do with planets. Instead, it's the result of a dying star's final gasps, a cosmic death scene playing out in the most beautiful and serene way imaginable. Picture an aging star, perhaps once similar to our Sun, reaching the end of its nuclear fuel supply. As the fusion reactions in its core begin to falter, the star starts to lose its battle against its own gravity. Its outer layers become unstable, puffing away into space in a series of gentle stellar exhalations. But here's where the Boomerang Nebula becomes extraordinary. The dying star at its center is expelling material at an incredible rate, losing mass equivalent to our Sun every 1,000 years. This expelled gas is racing away from the star at speeds of nearly 600,000 kilometers per hour, creating one of the most dramatic cooling events in the known universe. Gentle pause. Imagine yourself floating safely in space, watching this cosmic refrigeration process unfold. As the star's hot gas expands rapidly into the vacuum of space, it cools through a process called adiabatic expansion, the same principle that makes aerosol cans feel cold when you use them, but on a truly astronomical scale. The gas in the Boomerang Nebula is expanding so rapidly that it's cooling far below even the temperature of the cosmic microwave background. In essence, this dying star has created a region of space colder than the universe itself, a pocket of profound chill carved out of the cosmic warmth by the star's final act. What makes this cooling even more remarkable is its efficiency. The expanding gas doesn't just cool gradually, it plunges toward absolute zero with stunning rapidity. The nebula's temperature of 1 Kelvin means that the gas molecules within it are moving at only about 150 meters per second, barely faster than the speed of sound on Earth. Through our most powerful telescopes, the Boomerang Nebula appears as a beautiful, ethereal structure, sometimes described as bow-tie-shaped, sometimes as resembling a cosmic hourglass. The expelled gas creates flowing, sculpture-like forms as it interacts with the interstellar medium, carving graceful curves and loops that speak to the complex dynamics of stellar death. The nebula's name comes from its asymmetric shape, which reminded early observers of a boomerang when viewed through ground-based telescopes. Later observations with the Hubble Space Telescope revealed its true hourglass structure, showing streamers of gas flowing away from the central star like cosmic silk scarves dancing in an unfelt wind. But beyond its visual beauty lies the deeper marvel of its temperature. At 1 Kelvin, the Boomerang Nebula is so cold that any molecules present would be moving incredibly slowly. If there were water molecules in this environment, they would be frozen more solid than anything we can imagine on Earth. The molecular motion that gives rise to heat has been almost entirely drained away by the expansion process. What time is it where you are now? Have you settled deeper into your comfortable position as we've explored these cosmic wonders? Feel how your own body temperature is naturally dropping as you prepare for sleep, your personal version of cosmic cooling, preparing you for the deep rest that awaits. Scientists believe that the Boomerang Nebula's extreme cold is temporary in cosmic terms. As the expelled gas continues to expand and thin out, it will eventually reach equilibrium with the surrounding cosmic microwave background radiation. The profound chill we observe today represents a brief moment in the nebula's evolution, a snapshot of stellar death captured at its coldest point. Yet in human terms, this brief moment will last for thousands of years. The cooling process that created the Boomerang Nebula's record-breaking temperature will continue long after our civilization has evolved beyond recognition. It's a reminder of the vast timescales on which cosmic processes unfold and the patient persistence of natural phenomena. As you imagine this distant nebula, think of it as a cosmic meditation on letting go. The dying star at its center is releasing everything it once held dear, its outer layers, its warmth, its structured form, allowing them to expand into the infinite cold of space. In doing so, it creates something of unprecedented beauty and scientific fascination. There's something deeply peaceful about this image, a star finding serenity in its final moments, creating the coldest natural environment in the universe through the simple act of releasing its hold on material existence. It's a lesson in cosmic acceptance, in finding beauty and purpose even in endings. Chapter 4. The Physics of Extreme Cold. When matter transforms. To truly appreciate the coldest places in the universe, we need to understand what happens to matter when temperatures approach absolute zero. As substances become colder and colder, they undergo fascinating phase transitions that reveal the quantum mechanical nature of reality itself. On Earth, we're familiar with the basic states of matter, solid, liquid, and gas. Water freezes into ice, boils into steam, following predictable patterns based on temperature and pressure. But as we venture into the extreme cold of cosmic environments, matter begins to behave in ways that seem almost magical. Picture the molecules in any substance as tiny dancers. At high temperatures, they dance frantically, spinning and vibrating with tremendous energy. As the temperature drops, their dance becomes more sedate, more ordered. In solids, they settle into regular patterns, still vibrating but constrained to specific positions like dancers maintaining formation. But something extraordinary happens as we approach absolute zero. The quantum mechanical properties of matter, usually hidden by thermal noise, begin to dominate. Particles start to behave not like individual dancers, but like a perfectly synchronized chorus, moving in harmony according to the strange rules of quantum mechanics. At sufficiently low temperatures, certain materials undergo a phase transition to become what physicists call a Bose-Einstein condensate. In this state, thousands or even millions of atoms lose their individual identities and merge into a single quantum entity. They become, in effect, one giant atom with properties that can only be described by quantum mechanics. Peaceful pause. Imagine watching this transformation, individual particles gradually surrendering their separate existence to become part of a larger, unified whole. It's like watching countless individual snowflakes melt together to form a perfectly smooth, mirror-like surface of ice. But instead of melting, the particles are cooling into unity. In the coldest regions of space, particularly in the shadows of interstellar dust clouds or in the expanding gas of nebulae like the Boomerang, conditions might exist that allow for these exotic quantum states to form naturally. We don't yet have the instruments sensitive enough to detect them directly, but theoretical physics suggests they must exist. The behavior of matter at these extreme temperatures challenges our everyday intuitions about the nature of reality. Particles can exist in multiple states simultaneously, connected by quantum entanglement across vast distances. The boundary between individual objects becomes blurred, replaced by wave-like probability distributions that describe the likelihood of finding a particle in any given location. Consider helium-3, a rare isotope that becomes superfluid at temperatures below about 2.5 millikelvin, just thousandths of a degree above absolute zero. In this state, it can flow without friction, climb up the walls of containers, and exhibit other behaviors that seem to defy physics as we normally understand it. In the cosmic context, regions cold enough to support such phenomena might exist in the hearts of neutron stars, where matter is compressed to densities millions of times greater than anything on Earth while simultaneously being cooled by the expansion of space itself. The combination of extreme density and extreme cold could create conditions unlike anything we can reproduce in terrestrial laboratories. The quantum effects that emerge at ultra-low temperatures aren't just scientific curiosities. They reveal fundamental truths about the nature of matter and energy. They show us that beneath the apparent chaos of thermal motion lies an underlying order, a hidden harmony that becomes visible only when heat is removed and matter is allowed to find its most natural, most restful state. As you lie here now, feeling your body's natural cooling as you prepare for sleep, you're participating in your own version of this cosmic transition toward order and rest. Your metabolic processes are slowing. Your neural activity is shifting toward the synchronized patterns of sleep. Your entire being is finding its way to a more peaceful, more unified state. Where are you listening from tonight? Has the temperature in your room settled into that perfect range for sleep? Notice how your body naturally seeks the optimal thermal environment for rest. Not too hot, not too cold, but just right for the transition into dreams. Chapter 5. Laboratory created cold approaching absolute zero on Earth. While we explore the natural cold of cosmic environments, it's worth understanding how scientists on Earth have pushed the boundaries of cold, creating temperatures that are actually colder than anything found naturally in the universe. This achievement represents one of humanity's most remarkable technical accomplishments and gives us insight into what matter might be doing in the coldest cosmic environments. The quest to reach absolute zero began in the late 19th century with scientists like James Dewar and Heike Kamerlingh-Onnes, who first liquefied gases like oxygen, nitrogen, and eventually helium. Each breakthrough opened new windows into the behavior of matter at extreme temperatures and revealed phenomena that had never been observed before. Picture the early cryogenic laboratories as cosmic simulation chambers, where researchers created small pockets of space-like conditions right here on Earth. Using techniques like compression and expansion cycles, magnetic cooling, and laser cooling, they gradually pushed temperatures lower and lower, approaching the theoretical limit of absolute zero. Today, the coldest temperatures ever achieved on Earth are measured in billionths of a degree above absolute zero. Far colder than the cosmic microwave background, colder than the Boomerang Nebula, colder than anything known to exist naturally in the universe. These temperatures are so extreme that they can only be maintained for fractions of a second in carefully controlled laboratory conditions. The techniques used to achieve these temperatures are themselves marvels of physics and engineering. Laser cooling, for instance, uses precisely tuned light to slow down individual atoms. Imagine atoms as tiny cars speeding along a highway, and laser beams as gentle headwinds that gradually reduce their speed until they're barely crawling. When atoms move slowly enough, their temperature approaches absolute zero. Gentle pause. Magnetic cooling takes advantage of the quantum properties of atoms to remove thermal energy. Picture atoms as tiny magnets that can be aligned or randomized. When a strong magnetic field aligns them all in the same direction, removing the field allows them to randomize again, but in the process they give up thermal energy to their surroundings, cooling themselves down. Evaporative cooling, the technique used to create the coldest temperatures of all, works like cosmic evaporation in reverse. Just as a hot cup of coffee cools when its most energetic molecules escape as steam, a trapped gas of atoms can be cooled by allowing its most energetic particles to escape, leaving behind only the coldest, slowest moving atoms. The achievement of ultra-low temperatures has revealed phenomena that challenge our understanding of reality itself. At temperatures below a few millionths of a degree above absolute zero, certain gases form Bose-Einstein condensate states of matter where thousands of atoms behave as a single quantum entity. In these condensates, atoms lose their individual identities and merge into what physicists call a matter wave, a single quantum object that can be several millimeters across, while still maintaining the coherent properties of a single atom. It's as if the boundary between particle and wave, between individual and collective, simply dissolves at sufficiently low temperatures. Even more remarkably, these ultracold atoms can be made to form what are called optical lattices, regular arrangements held in place by intersecting laser beams. These artificial crystals of light and matter allow scientists to study quantum mechanics in ways that were previously impossible, creating tabletop experiments that simulate the behavior of matter under extreme cosmic conditions. The coldest temperatures achieved in laboratories approach what's called the quantum regime, where thermal energy becomes so small that quantum mechanical effects dominate completely. In this regime, particles can tunnel through barriers that should be impenetrable, exist in multiple locations simultaneously, and exhibit correlations that Einstein famously called spooky action at a distance. What's particularly beautiful about these achievements is that they represent a kind of technological meditation, the patient, methodical removal of chaos and heat until only the most fundamental quantum order remains. Scientists have learned to create small pockets of perfect stillness, regions where matter exists in its most basic, most peaceful state. As you prepare for sleep tonight, consider that your body is also finding its own version of this cosmic stillness. Your heart rate is slowing, your breathing is deepening, your neural activity is settling into the synchronized patterns that characterize deep rest. You're naturally approaching your own biological equivalent of absolute zero, not in temperature, but in the quieting of metabolic chaos and the emergence of restful order. Are you feeling more relaxed now than when we began this journey? Have your muscles softened, your thoughts become more dreamlike? You're experiencing your own transition toward the kind of profound rest that matter finds at ultra-low temperatures. Chapter 6. The Oort Cloud, the Solar System's Frozen Frontier. Let's journey to the very edge of our solar system, to a vast spherical shell of icy objects called the Oort Cloud. Named after the Dutch astronomer Jan Oort, who first proposed its existence, this distant realm represents one of the coldest environments in our local cosmic neighborhood. The Oort Cloud extends from about 2,000 to 200,000 astronomical units from the Sun. That's roughly 50 times farther than Pluto at its most distant point, and nearly halfway to the nearest star. At these tremendous distances, the Sun appears as nothing more than a bright star among many others, providing virtually no heat to warm the countless icy bodies that call this region home. Picture yourself drifting through this cosmic deep freeze, surrounded by billions of comet nuclei in a slow, stately dance around our distant Sunday. Each of these objects is a time capsule from the early solar system, a pristine sample of the materials from which the planets formed 6 billion years ago, preserved by the profound cold of interstellar space. The temperature in the Oort cloud hovers around 5 Kelvin, barely warmer than the cosmic microwave background radiation that permeates all of space. At these temperatures, water ice becomes harder than granite, and gases that we consider permanent fixtures of our atmosphere, nitrogen, oxygen, carbon dioxide, would be frozen solid for billions of years. Peaceful pause. What makes the Oort cloud particularly fascinating is its stability. Unlike the dynamic, chaotic environments closer to stars, where gravitational forces and radiation create constant change, the Oort cloud exists in a state of profound tranquility. The objects within it move in stately, predictable orbits that have remained essentially unchanged since the formation of the solar system. Imagine the patience of these icy worlds, spending billions of years in the cosmic deep freeze, occasionally stirred by the gravitational influence of passing stars or molecular clouds. When such perturbations do occur, they can send a comet on a long journey toward the inner solar system, where it will briefly blaze across our skies before returning to the frozen depths of space. The Oort cloud represents more than just cold storage for ancient ice. It's a vast reservoir of the original materials from which our solar system formed. The comet nuclei within it contain pristine samples of the dust and gas that existed in the solar nebula before the Sun ignited and the planets coalesced. They're frozen libraries of cosmic history, each one preserving information about conditions in the early solar system. Recent computer simulations suggest that the Oort cloud might contain trillions of comet nuclei, with a total mass several times that of Earth. This makes it one of the most massive components of our solar system, yet also one of the most diffuse. The average distance between objects in the Oort cloud is measured in astronomical units, typically several times the distance from Earth to the Sun. The profound cold of the Oort cloud has preserved these objects in near-perfect condition for billions of years. Unlike the rocky planets, which have been heated, differentiated, and geologically processed, or the gas giants, which have undergone complex atmospheric evolution, the comet nuclei of the Oort cloud remain essentially unchanged from their primordial state. When astronomers study comets that originate from the Oort cloud, they're looking at time machines, objects that carry information about the chemical composition, temperature, and physical conditions that existed during the birth of our solar system. The profound cold of this distant realm has made these scientific treasures possible. Think about the scale of time involved here. The objects in the Oort cloud have been patiently waiting in the cosmic deep freeze for longer than multicellular life has existed on Earth. They've maintained their vigil through the entire history of complex life on our planet, preserving their ancient secrets in the profound stillness of interstellar cold. What time is it where you are listening tonight? As the evening has progressed and the hours have passed, have you felt yourself settling deeper into relaxation? Just as the Oort cloud exists in a state of profound cosmic patience, you too can find that deep, restful stillness that comes with true relaxation. The Oort cloud also serves as our solar system's interface with interstellar space. Beyond its outer boundary lies the realm of other stars, other planetary systems, other worlds that may harbor their own versions of life and intelligence. The cold objects of the Oort cloud are the sentinels that mark the frontier between our cosmic home and the vast unknown. As you imagine these distant, frozen worlds, let their profound tranquility wash over you. They exist in a state of perfect rest, undisturbed by the chaos and activity of the inner solar system, patiently maintaining their ancient orbits in the cosmic deep freeze. There's something deeply peaceful about this image, billions of objects finding harmony in the cold and darkness, each one following its own perfect trajectory through space and time. Chapter 7. Neutron stars and stellar remnants, hot cores, cold surfaces. Now let's explore one of the universe's most extreme contradictions, neutron stars. Objects that can simultaneously harbor some of the hottest and coldest environments known to science. These collapsed stellar cores represent the endpoint of stellar evolution for stars too massive to become white dwarfs but not quite massive enough to form black holes. Picture a star perhaps 10 to 20 times more massive than our Sun reaching the end of its nuclear fuel supply. As the fusion reactions in its core sputter and die, gravity finally wins its billion-year battle against the star's internal pressure. The core collapses catastrophically, compressing matter to densities so extreme that protons and electrons are crushed together to form neutrons. The result is an object about 20 kilometers across, roughly the size of a city, but containing more mass than our entire Sunday. A teaspoon of neutron star material would weigh as much as a mountain on Earth. These objects represent matter compressed to the very limits of what the laws of physics allow. But here's where the temperature story becomes fascinating. When a neutron star first forms in the collapse of a massive star, its core temperature can reach 100 billion Kelvin, hotter than the interior of any main sequence star, hot enough that the very notion of atomic structure breaks down completely. At these temperatures, matter exists in states that we can barely imagine, possibly including exotic particles like hyperons and kaons. Gentle pause. Yet as we move outward from this blazing core, temperatures drop dramatically. The neutron star's surface, despite being heated by the incredibly hot interior, can cool to temperatures of just a few million Kelvin, and in the case of the oldest neutron stars, potentially much colder. Imagine yourself observing this cosmic contradiction from a safe distance. At the neutron star's center, temperatures rage that would vaporize any known material instantly. But move just a few kilometers outward to the surface, and you encounter conditions that, while still incredibly hot by human standards, are actually quite cool for stellar objects. The cooling process of neutron stars reveals some of the most beautiful physics in the universe. These objects cool through several mechanisms. They radiate photons from their surface, emit neutrinos from their interior, and may even cool through the formation of exotic matter phases in their cores. Neutrino cooling is particularly fascinating. Neutrinos are ghostly particles that barely interact with normal matter. Trillions of them pass through your body every second without you noticing. But in the extreme environment of a neutron star's interior, neutrino production becomes so efficient that these elusive particles carry away enormous amounts of thermal energy, cooling the neutron star far more rapidly than surface radiation alone could accomplish. The oldest neutron stars in our galaxy, formed billions of years ago, may have surface temperatures of just a few 100,000 Kelvin. While this is still incredibly hot by human standards, hot enough to vaporize any material we know, it's remarkably cool for a stellar object. These ancient neutron stars represent some of the most efficiently cooled objects in the universe. But the temperature story doesn't end there. Some neutron stars possess magnetic fields trillions of times stronger than Earth's magnetic field. These magnetars can heat their surfaces through magnetic reconnection events, temporarily raising surface temperatures to tens of millions of degrees. It's as if the neutron star's magnetic field acts as a cosmic heating element, occasionally rewarming the cooling surface. The interplay between heating and cooling on neutron star surfaces creates complex temperature patterns. Some regions may be significantly hotter than others, creating hot spots that can be observed as the neutron star rotates. These temperature variations tell us about the star's magnetic field structure, its internal composition, and its thermal history. What's particularly remarkable is that neutron stars can maintain steep temperature gradients over relatively small distances. The difference between the blazing core and the cooler surface represents one of the most extreme temperature contrasts found anywhere in the universe. A difference of billions of degrees compressed into a space smaller than most cities. Where are you right now as you listen to this cosmic temperature story? Are you comfortably warm under blankets, or perhaps feeling the cool night air? The temperature differences you experience in your environment, while important for your comfort, are infinitesimal compared to the thermal extremes we find in neutron stars. As neutron stars age and continue to cool, they may eventually reach surface temperatures comparable to those found in other cold cosmic environments. The oldest neutron stars might have surface temperatures of just tens of thousands of Kelvin, still hot by human standards, but approaching the realm of temperature where the quantum effects we discussed earlier begin to dominate matter's behavior. The cooling neutron star represents a kind of cosmic meditation on time and patience. Over billions of years, these incredibly dense objects gradually surrender their thermal energy to space, slowly cooling from their initial blazing temperatures toward a more peaceful, more stable state. It's a process that will continue for longer than the current age of the universe, a slow cosmic exhale that speaks to the patient persistence of physical law. Chapter 8: Brown Dwarfs, the Failed Stars of Cosmic Winter. Let's now explore one of the universe's most intriguing inhabitants, brown dwarfs, objects that represent a middle ground between planets and stars, and some of the coolest stellar mass objects we know. These failed stars offer us a window into cosmic environments where the usual rules of stellar physics break down and exotic forms of matter behavior emerge. Brown dwarfs form much like regular stars, condensing from collapsing clouds of gas and dust. But they lack sufficient mass to sustain the nuclear fusion reactions that power true stars. Instead of igniting into brilliant suns, they settle into a twilight existence, slowly radiating away their formation heat over billions of years. Picture these objects as cosmic embers, still warm from the fires of their birth, but gradually cooling as they drift through space. The most massive brown dwarfs, just below the threshold for sustained fusion, can maintain surface temperatures of 2,000 to 3,000 Kelvin for millions of years. But the smallest, least massive brown dwarfs cool much more rapidly, eventually reaching temperatures comparable to the giant planets in our own solar system. The coolest brown dwarfs we've discovered have surface temperatures around 250 Kelvin, colder than the freezing point of water. At these temperatures, water vapor in their atmospheres can condense into clouds, just like the water clouds in Earth's atmosphere. But these aren't ordinary clouds. They exist around objects with masses dozens of times greater than Jupiter, creating weather systems unlike anything in our solar system. Peaceful pause. Imagine floating above one of these ultra-cool brown dwarfs, observing clouds of water vapor drifting through an atmosphere heated only by the fading warmth of gravitational contraction. The surface below glows with a dull red heat, barely visible to human eyes, while above you stretch clouds that might not look entirely unfamiliar to someone who has watched Earth's weather from space. But brown dwarf atmospheres can host even more exotic phenomena. In the coolest examples, the temperatures drop low enough for unusual compounds to condense out of the gas phase. We might find clouds of liquid iron, storms of molten glass, or precipitation of exotic compounds that can't exist in liquid form anywhere on Earth. The study of brown dwarfs has revealed a surprising diversity of atmospheric conditions. Some have relatively clear atmospheres that allow us to peer deep into their structure. Others are shrouded in thick clouds that hide their surfaces from view. The atmospheric dynamics of these objects create complex weather patterns, storms that can rage for years, bands of circulation that redistribute heat around the globe, and temperature variations that change as the brown dwarf rotates. One of the most remarkable things about brown dwarfs is their longevity. While massive stars burn through their nuclear fuel in millions of years, and even sun-like stars will exhaust their hydrogen in about 10 billion years, brown dwarfs can continue to radiate heat for trillions of years. They're among the longest-lived objects in the universe, slowly cooling through temperatures that span the entire range from stellar to planetary. This extended cooling process means that brown dwarfs serve as cosmic thermometers, recording the thermal history of their local galactic environment. The oldest brown dwarfs in our galaxy have been cooling for nearly as long as the universe has existed, gradually settling toward temperatures that approach the cosmic microwave background itself. As brown dwarfs cool, their atmospheric chemistry undergoes dramatic changes. Compounds that were dissociated into individual atoms at high temperatures begin to form molecules as temperatures drop. Water, methane, ammonia, and more complex organic compounds can all appear in brown dwarf atmospheres as they cool through specific temperature ranges. The coolest brown dwarfs represent laboratories for studying matter under conditions that are difficult to recreate on Earth. Their atmospheric pressures can be thousands of times greater than Earth's atmospheric pressure, while their temperatures span the range from red-hot to ice-cold. This combination creates opportunities for exotic chemistry and physics that we're only beginning to understand. What's particularly fascinating is that the coolest brown dwarfs blur the boundary between stars and planets. They have masses like stars but temperatures like planets. Their atmospheric compositions can resemble those of giant planets, while their magnetic fields and internal structure are more star-like. They challenge our traditional categories and force us to think more flexibly about the nature of cosmic objects. Recent discoveries have identified brown dwarfs so cool that their surface temperatures are comfortable by human standards, around room temperature or slightly cooler. These objects, while still radiating heat from their formation billions of years ago, have cooled to the point where a human could theoretically survive on their surface without protective heating, though the lack of oxygen and crushing atmospheric pressure would present other challenges. Are you feeling comfortable where you are right now? What's the temperature like in your environment? As you listen to these descriptions of cosmic cold, notice how your own body temperature provides a perfect reference point for understanding these extreme environments. You exist in a narrow temperature range that allows for the complex chemistry of life, while brown dwarfs span temperature ranges that encompass everything from stellar fire to interplanetary cold. The study of ultra-cool brown dwarfs has opened new windows into understanding planetary atmospheres as well. Many of the atmospheric processes we observe in the coolest brown dwarfs, cloud formation, atmospheric circulation, chemical equilibrium, also occur in the giant planets of our own solar system and in the exoplanets orbiting other stars. As these cosmic embers continue their slow fade toward absolute zero, they serve as patient laboratories for studying matter under extreme conditions. Each brown dwarf is conducting its own multi-billion-year experiment in atmospheric physics, slowly cooling through temperature regimes that reveal different aspects of chemistry and thermodynamics. The profound timescales involved in brown dwarf cooling mirror the deep patience of cosmic evolution itself. These objects will continue to radiate heat long after our Sun has exhausted its nuclear fuel and died. They represent one of the universe's most enduring forms, slowly transitioning from the realm of stellar objects towards something more akin to massive, lonely planets drifting through the cosmic dark. Chapter 9. The Shadows of Space Cold Traps and Molecular Clouds. Now let's explore some of the universe's most hidden cold regions. The shadowed areas where starlight never reaches and matter can achieve temperatures that rival laboratory-created extremes. These cosmic cold traps exist in the shadows of dust clouds, in the polar regions of planets and moons, and in the vast molecular clouds where new stars are born. In our own solar system, some of the coldest natural temperatures occur in permanently shadowed regions near the poles of planets and moons. On Mercury, despite its proximity to the Sun, the floors of polar craters that never see sunlight can reach temperatures as low as 25 Kelvin, colder than the surface of Pluto. Picture these shadowed regions as cosmic refrigerators, places where the absence of solar heating allows matter to radiate away its thermal energy into the infinite cold of space. In these shadows, water ice can persist for billions of years, creating permanent frost deposits that serve as repositories for the solar system's water inventory. The Moon's polar regions contain similar cold traps, where temperatures can drop to around 40 Kelvin in areas that have been shielded from sunlight for geological ages. These regions may contain billions of tons of water ice, delivered by ancient comet impacts and preserved by the profound cold of permanent shadow. Gentle pause. But the most extensive cold regions in the universe are the giant molecular clouds, vast assemblages of gas and dust that drift through interstellar space, serving as the birthplaces of new stars and planetary systems. These clouds can be hundreds of light-years across and contain enough material to form thousands of stars like our Sun. Within the densest regions of molecular clouds, where dust grains block nearly all starlight, temperatures can drop to just 10 Kelvin, approaching the realm of the coldest natural environments we know. At these temperatures, most gases freeze onto the surfaces of dust grains, creating icy mantles that preserve simple molecules in crystalline form. Imagine drifting through one of these cosmic winter wonderlands, surrounded by dust grains coated with frozen water, carbon monoxide, methanol, and more complex organic compounds. The profound cold has turned the interstellar medium into a vast chemical laboratory, where slow chemical reactions proceed over millions of years to create the molecular building blocks of future planetary systems. The chemistry that occurs in these cold clouds is unlike anything we observe in warmer environments. At temperatures near 10 Kelvin, molecules move so slowly that reaction rates are governed by quantum tunneling rather than thermal motion. Hydrogen atoms can tunnel through energy barriers that would be insurmountable at higher temperatures, allowing for the formation of molecular hydrogen, the most abundant molecule in the universe. This process of quantum tunneling at ultra-low temperatures reveals the deep connection between cosmic cold and quantum mechanics. In the coldest regions of molecular clouds, matter behaves according to purely quantum rules, with particles existing in superposition states and exhibiting wave-like properties that become crucial for chemical bonding. The dust grains within molecular clouds serve as tiny surfaces where cosmic chemistry unfolds. These grains, typically smaller than the particles in cigarette smoke, provide meeting places where atoms and molecules can stick together long enough to form chemical bonds. The extreme cold ensures that once molecules form on grain surfaces, they remain stable for millions of years. Over time, these grain surface reactions build up complex organic molecules, including some of the precursors to the amino acids and nucleotide bases that form the foundation of life as we know it. The cold chemistry of molecular clouds may be responsible for seeding the universe with the organic compounds that eventually lead to the emergence of life on suitable planets. Where are you listening from tonight? Has the temperature around you settled into that perfect range for comfort and rest? Notice how your environment maintains just the right conditions for the complex chemistry of life to continue within your own body, while the molecular clouds were exploring showcase chemistry at the opposite extreme, ultra-slow, ultra-cold processes that unfold over cosmic timescales. The largest molecular clouds in our galaxy contain regions where the temperature approaches the cosmic microwave background itself, around 2.7 Kelvin. In these coldest regions, thermal energy becomes so minimal that even the slightest external influences, the pressure of starlight, the magnetic fields that thread through space, the gravitational effects of distant objects, become important factors in determining how matter behaves. These ultra-cold regions within molecular clouds may represent some of the most pristine environments in the universe, places where matter exists in states closer to absolute zero than anywhere else we know. They're cosmic deep freezers that preserve samples of the primordial gas from which the first stars formed, maintaining chemical compositions that date back to the early universe. As molecular clouds evolve and eventually give birth to new star systems, these cold regions play a crucial role in determining the chemical composition of the resulting planets. The molecules formed in the profound cold of prestellar cores become incorporated into the disks of gas and dust from which planets eventually coalesce. The study of cold chemistry in molecular clouds has revealed that the universe is far more chemically active than we once imagined. Even in regions where average temperatures approach absolute zero, slow but steady chemical processes continue to build molecular complexity, creating an inventory of organic compounds that will eventually be inherited by new planetary systems. Chapter 10: White Dwarfs, the Cosmic Diamonds in Deep Freeze. Let's turn our attention to white dwarf stars, the final fate awaiting our own sun and about 97% of all stars in the galaxy. These incredibly dense stellar remnants begin their existence at temperatures exceeding 100,000 Kelvin, but over billions of years, they cool to become some of the coldest stellar objects in the universe, eventually crystallizing into cosmic diamonds. Picture a white dwarf as the exposed core of a former star, no longer generating energy through nuclear fusion but still radiating the heat accumulated over millions of years of stellar burning. These objects pack roughly the mass of our Sun into a sphere about the size of Earth, creating matter so dense that a teaspoon would weigh as much as an automobile. When a star like our Sun exhausts its nuclear fuel, it expels its outer layers to form a planetary nebula, leaving behind the hot, compressed core that becomes a white dwarf. Initially, these stellar remnants shine with surface temperatures around 150,000 Kelvin, much hotter than the surface of the Sun. But with no internal energy source to maintain this heat, they begin a slow, inexorable cooling process that will continue for trillions of years. The cooling of white dwarfs follows a predictable pattern that makes them excellent cosmic chronometers. By measuring a white dwarf's temperature and comparing it to theoretical cooling models, astronomers can determine how long ago the star died and began its cooling journey. This technique has allowed us to estimate the ages of some of the oldest stellar populations in our galaxy. Peaceful pause. As white dwarfs cool below about 4,000 Kelvin, roughly the same temperature as a red dwarf star's surface, something remarkable begins to happen in their interiors. The extreme density and pressure, combined with the decreasing temperature, create conditions where the carbon and oxygen atoms that make up most of the white dwarf's mass begin to arrange themselves into crystalline structures. Imagine the interior of a cooling white dwarf gradually transforming from a dense gas of individual atoms into a solid crystal, but a crystal made of carbon and oxygen atoms packed so tightly that it's millions of times denser than any diamond found on Earth. This crystallization process releases a small amount of additional heat, slightly slowing the white dwarf's cooling rate and extending its observable lifetime. The crystallization of white dwarfs represents one of the universe's most spectacular phase transitions. Deep within these cooling stellar remnants, cosmic diamonds are forming crystalline structures of carbon atoms arranged in perfect three-dimensional lattices, but compressed to densities that exceed anything possible in terrestrial materials. These crystalline white dwarfs will continue cooling for far longer than the current age of the universe. The coolest white dwarfs we've discovered have surface temperatures around 3000 Kelvin, and they're already billions of years old. But theoretical models predict that white dwarfs will continue to cool and dim for more than 100 billion years, eventually reaching temperatures comparable to the cosmic microwave background. In the far future, when the last red dwarf stars have finally exhausted their fuel and died, crystalline white dwarfs will be among the few remaining sources of heat in a universe that has grown cold and dark. These cosmic diamonds will continue to radiate their stored thermal energy into space, serving as beacons of warmth in an otherwise frozen cosmos. The study of white dwarf cooling has revealed unexpected complexities in their thermal evolution. Some white dwarfs show evidence of additional heating from gravitational settling, where heavier elements sink toward the center while lighter elements rise to the surface. Others may have thin hydrogen or helium atmospheres that affect their cooling rates, creating insulating layers that slow the escape of heat from their crystalline cores. Recent discoveries have identified white dwarfs with surface temperatures as low as 2700 Kelvin, cool enough that their surfaces would appear deep red to human eyes, glowing like cosmic embers in the darkness of space. These ultra-cool white dwarfs represent some of the oldest objects in our galaxy, stellar corpses that have been cooling since the universe was young. What's particularly beautiful about white dwarf cooling is its inevitability and universality. Nearly every star in the universe will eventually become a white dwarf, unless it's massive enough to explode as a supernova or collapse into a black hole. This means that the far future of our cosmos will be populated by trillions of these cooling crystalline objects, each one a diamond in space, slowly radiating the last heat from their stellar pasts. Are you feeling the natural cooling that comes with approaching sleep? Just as white dwarfs gradually transition from hot, energetic objects to cool, crystalline remnants, your body is undergoing its own natural cooling process as your metabolism slows and prepares for rest. There's something profoundly peaceful about these cosmic cooling processes. They speak to the natural tendency of all systems to find their most stable, most restful states. The existence of crystalline white dwarfs also connects to some of the exotic physics we discussed earlier. At the extreme densities found in white dwarf interiors, matter exists in states that approach the quantum degeneracy we see in laboratory-created ultra-cold gases. The electrons in white dwarf matter form what's called a degenerate electron gas, where quantum effects dominate over thermal effects even at relatively high temperatures. As white dwarfs continue to cool toward absolute zero, their crystalline lattices will eventually reach the point where quantum effects become dominant even for the atomic nuclei. At these ultra-low temperatures, the vibrational modes of the crystal lattice will freeze out one by one, leaving behind a perfect quantum crystal, a macroscopic object exhibiting purely quantum mechanical behavior. Chapter 11. The Intergalactic Void Cold Beyond Imagination. Now let's venture beyond our galaxy, beyond clusters of galaxies, into the vast intergalactic voids, regions of space so empty and so far from any source of heat that they represent some of the coldest environments in the entire universe. These cosmic deserts stretch across hundreds of millions of light years, containing almost nothing but the faint afterglow of creation itself. Picture yourself floating in the middle of such a void, surrounded by emptiness so profound that the nearest galaxy appears as nothing more than a faint smudge of light, billions of light years away. In every direction, space stretches endlessly with an average density of perhaps one hydrogen atom per cubic meter, a vacuum more perfect than anything we can create in terrestrial laboratories. In these intergalactic voids, matter exists at temperatures that approach the cosmic microwave background radiation itself, around 2.7 Kelvin. But in the most empty regions, even this faint heat from the Big Bang's afterglow is diluted by the ongoing expansion of space, creating pockets where temperatures may drop slightly below the average CMB temperature. The intergalactic medium in these voids consists primarily of primordial hydrogen and helium, left over from the universe's early nuclear synthesis. This gas is so tenuous that individual atoms might travel for millions of years without encountering another particle. In such an environment, the very concept of temperature becomes almost meaningless. How do you measure the thermal motion of particles when they rarely interact? Gentle pause. What makes these voids particularly remarkable is their stability. Unlike regions near galaxies and stars, where gravitational forces, stellar winds, and cosmic ray bombardment create dynamic, changing conditions, the intergalactic voids exist in a state of profound cosmic peace. The matter within them has remained essentially undisturbed since the early epochs of cosmic evolution. In these cold, empty regions, the few atoms that do exist move through space at velocities determined primarily by the universe's overall expansion rather than by thermal motion. They participate in the grand cosmic recession, carried along by the stretching of space itself rather than by the random thermal motions that characterize matter in warmer environments. The magnetic fields that thread through these voids are incredibly weak, billions of times weaker than Earth's magnetic field, and trillions of times weaker than the fields in more active cosmic environments. This creates conditions of almost perfect isolation, where individual particles can maintain quantum coherence over scales that would be impossible in denser environments. Some theoretical models suggest that in the emptiest parts of intergalactic voids, conditions might exist that allow for the formation of exotic quantum states, regions where the few scattered atoms exist in superposition states or exhibit quantum entanglement across vast distances. These would represent naturally occurring quantum systems on scales far larger than anything we can create in laboratories. The profound emptiness of intergalactic voids also makes them natural laboratories for studying dark matter and dark energy. Without the gravitational clumping that characterizes regions near galaxies, these voids provide clean environments where the subtle effects of dark energy's cosmic acceleration can be observed and measured. As the universe continues to expand and accelerate, driven by the mysterious dark energy that comprises about 70% of the cosmic energy budget, these voids will become even larger and emptier. The few atoms they contain will be stretched farther apart, and their already minimal temperatures will drop even closer to absolute zero. In the far future, perhaps 100 billion years from now, the accelerating expansion of space will have carried galaxies so far apart that beings living in one galaxy will no longer be able to see any others. The universe will appear to be nothing but a single galaxy surrounded by an infinite, empty void, a cosmic winter that will last far longer than the current age of the universe. But even in this future cosmic winter, the intergalactic voids will not be completely empty. They'll still contain the cosmic microwave background radiation, though stretched and cooled by billions of additional years of expansion. They'll also contain the mysterious dark matter that helps shape the universe's large-scale structure, though it will be spread so thinly as to be essentially undetectable. Where are you right now as you contemplate these vast, empty spaces? What time has it become as we've journeyed through these cosmic extremes? The emptiness and cold of intergalactic voids might seem intimidating, but there's also something profoundly peaceful about them, regions of space where the chaos and violence that characterize more active cosmic environments have given way to perfect stillness and tranquility. The study of intergalactic voids has revealed that even in the coldest, emptiest regions of space, subtle structures and processes continue. Faint filaments of dark matter thread through the voids, creating a cosmic web that connects all the matter in the universe. These filaments are so tenuous that they're nearly impossible to detect, but they represent the underlying skeleton upon which all cosmic structure is built. Recent observations have also revealed that some intergalactic voids contain faint streams of gas that may be the remnants of ancient galactic interactions. These fossil streams preserve information about cosmic events that occurred billions of years ago, frozen in the profound cold of intergalactic space like cosmic ice cores that record the history of the universe's evolution. The intergalactic voids remind us that emptiness and cold are not simply the absence of something interesting. They're fundamental aspects of cosmic reality that reveal important truths about the nature of space, time, and matter. In their profound stillness, we glimpse the universe's natural tendency toward maximum entropy, the final state toward which all cosmic evolution is tending. Chapter 12: Rogue Planets, Wanderers in the Cosmic Cold. Let's explore one of the universe's most lonely inhabitants, rogue planets. Worlds that have been ejected from their birth solar systems and now wander through interstellar space, bathed only in the faint light of distant stars and the cosmic microwave background radiation. These cosmic orphans offer us a glimpse into planetary environments at the absolute limits of cold and isolation. Rogue planets form like normal planets, condensing from the disk of gas and dust that surrounds a young star. But gravitational interactions, perhaps with other planets, passing stars, or the complex dynamics of multiple star systems, can eject them from their home systems, sending them drifting alone through the galaxy. Picture a world that once knew the warmth of a nearby star, perhaps even harboring oceans and an atmosphere conducive to life, suddenly cast into the infinite night of interstellar space. Within a few million years of ejection, such a planet would cool to temperatures determined entirely by its internal heat and the faint cosmic background radiation. For a rocky planet like Earth, ejection into interstellar space would be catastrophic for any surface-based life. The surface temperature would quickly drop to around 3 Kelvin, just slightly above absolute zero, cold enough to freeze the atmosphere itself into layers of solid nitrogen, oxygen, and carbon dioxide coating the planet's surface. But the story becomes more interesting when we consider larger planets, gas giants like Jupiter or Neptune, that retain significant internal heat sources. These worlds generate energy through the slow gravitational compression of their interiors, a process that can continue for billions of years even in the absence of stellar heating. Peaceful pause. Imagine a rogue gas giant drifting through the space between stars, its upper atmosphere radiating heat into the cosmic void, while its interior continues to generate energy through gravitational contraction. The surface temperature of such a world might stabilize around 30 to 50 Kelvin, still incredibly cold, but potentially warm enough to maintain liquid regions beneath thick layers of surface ice. Recent computer models suggest that rogue planets with substantial atmospheres and internal heat sources might be able to maintain subsurface oceans for billions of years. These hidden seas would exist beneath kilometers of ice, warmed by the planet's internal heat and protected from the cosmic cold by their insulating covering. Such worlds would represent completely alien environments, planets where the energy cycle is driven entirely by internal processes rather than stellar radiation. Any life that might exist in their hidden oceans would have evolved in complete darkness, deriving energy from chemical processes rather than photosynthesis. The study of rogue planets has revealed that they might be surprisingly common. Some estimates suggest there could be billions of these wandering worlds in our galaxy alone, outnumbering planets that orbit stars. They represent a vast population of hidden worlds, each one a unique experiment in planetary evolution under extreme conditions. The surfaces of rogue planets would be among the most alien environments imaginable. With no stellar radiation to drive weather systems, the only atmospheric dynamics would be powered by internal heat sources. Convection from the planet's interior might create slow, massive atmospheric circulations, while the interaction between internal heat and the cosmic cold could generate unique forms of condensation and precipitation. On a rogue planet, weather might consist of the sublimation and refreezing of atmospheric gases, creating slow cycles of atmospheric renewal powered by the planet's internal temperature variations. Snow might fall upward as warm gases rise from the interior and condense in the upper atmosphere, while surface frosts might sublime directly into space when they encounter regions warmed by internal heat. The magnetic fields of rogue planets would create fascinating interactions with the interstellar medium. As these worlds travel through space, their magnetospheres would sweep up charged particles from the galactic cosmic ray background, potentially creating aurora displays in their upper atmospheres, ghostly lights visible only in radio wavelengths, painting these lonely worlds with invisible colors derived from their motion through space. What's particularly poignant about rogue planets is their isolation. A being standing on the surface of such a world would see a night sky completely unlike anything visible from Earth. Instead of a nearby sun dominating the sky, there would be only the faint light of distant stars thousands of times dimmer than moonlight on Earth. The galaxy itself might be visible as a faint band of light across the sky, but individual stars would appear as nothing more than points of light, providing no meaningful illumination. Are you feeling a sense of peaceful isolation as you listen to this description of cosmic wanderers? There's something both melancholy and beautiful about these solitary worlds, planets that have found a different path through the universe, discovering their own forms of stability and beauty in the profound cold of interstellar space. The discovery of rogue planets has expanded our understanding of what constitutes a habitable environment. These worlds demonstrate that life might find ways to survive and thrive even in the absence of stellar radiation, relying instead on internal planetary processes and the complex chemistry that can occur at the interfaces between liquid water, rocky surfaces, and exotic atmospheric conditions. Some of the most interesting rogue planets might be super-Earths, rocky worlds several times more massive than our planet. Such worlds would retain their internal heat longer than smaller planets, and their stronger gravitational fields might help them maintain thicker atmospheres even in the cold of interstellar space. The atmospheres of massive rogue planets could potentially maintain greenhouse effects strong enough to keep surface temperatures above the freezing point of water, at least in some regions. These worlds might harbor unique ecosystems based on chemosynthetic life forms that derive energy from the chemical reactions occurring at the interface between the planet's warm interior and its cold surface. As our galaxy continues to evolve, gravitational interactions will eject more planets from their birth systems, adding to the population of rogue worlds wandering through interstellar space. Each ejected planet carries with it a unique history, the chemical composition of its birth system, the particular dynamics that led to its ejection, and potentially the frozen remnants of any life that might have existed before its exile. Chapter 13. The Cosmic Web's Cold Filaments. Let's explore the large-scale structure of the universe itself. The cosmic web of dark matter filaments that connect galaxies across billions of light-years. While these filaments are invisible to ordinary light, they represent some of the most extensive cold structures in the universe, threading through space like a three-dimensional spider web made of exotic matter. The cosmic web emerged from tiny quantum fluctuations in the early universe, microscopic variations in density that were stretched to enormous scales by cosmic inflation. Over billions of years, gravity amplified these fluctuations, causing matter to flow along preferred directions and creating the web-like pattern of structure we observe today. Picture the universe as a vast foam, with galaxies and galaxy clusters located at the intersections of bubble walls, while the interior of the bubbles, the cosmic voids we discussed earlier, remain largely empty. The walls of this cosmic foam are the filaments of the cosmic web, containing most of the universe's dark matter along with streams of ordinary matter flowing between gravitational wells. The temperature of matter in these cosmic filaments is determined by a complex interplay of gravitational heating and cosmic expansion cooling. As matter falls into the gravitational potential wells created by dark matter concentrations, it heats up through gravitational compression. But the ongoing expansion of space works to cool this matter, creating temperature profiles that vary along the length of each filament. Gentle pause. In the coldest parts of cosmic filaments, regions far from galaxy clusters where gravitational heating is minimal, ordinary matter can exist at temperatures as low as 10 to 100 Kelvin. These regions contain primarily hydrogen and helium gas left over from the Big Bang, preserved in a nearly primordial state by the profound cold of intergalactic space. The dark matter that dominates these filaments exists at even lower effective temperatures. Dark matter particles, whatever they might be, interact so weakly with ordinary matter and radiation that they can maintain extremely cold temperatures even in regions where ordinary matter is being heated by gravitational processes. Recent theoretical models suggest that dark matter in the coldest cosmic filaments might exist in quantum states that approach absolute zero. If dark matter particles are their own antiparticles, they might form Bose-Einstein condensates in the most underdense regions of space, creating macroscopic quantum objects that span thousands of light-years. The study of cosmic filaments has revealed that they serve as highways for matter transport throughout the universe. Cold gas flows along these structures, feeding the growth of galaxies and carrying chemical elements forged in stellar cores to regions where new star formation can occur. The filaments act as both refrigerators and distribution networks, cooling and transporting matter across cosmic distances. Within cosmic filaments, we find some of the universe's most tenuous matter gas so diffuse that its density is millions of times lower than the best vacuums we can create on Earth. Yet this matter plays a crucial role in cosmic evolution, serving as the reservoir from which galaxies continue to grow and form new stars. The intersection points of cosmic filaments, the nodes where multiple strands of the cosmic web come together, are where we find galaxy clusters, the largest gravitationally bound structures in the universe. But between these nodes, along the quiet stretches of individual filaments, matter exists in states of profound isolation and cold. Observations of distant quasars have revealed the presence of these cold cosmic filaments through the absorption lines they create in quasar spectra. As light from distant quasars travels through the filaments, cold hydrogen gas absorbs specific wavelengths, creating a forest of absorption lines that maps the distribution of matter along our line of sight. This technique, known as the Lyman alpha forest, has shown us that cosmic filaments extend across the entire observable universe, creating a web of cold matter that connects all the galaxies we can see. It's a profound reminder that even the emptiest seeming regions of space are threaded with structures that participate in the universe's ongoing evolution. The cosmic web also creates some of the universe's most extreme temperature contrasts. A cosmic filament might contain cold hydrogen gas at 10 Kelvin flowing directly toward a galaxy cluster where shock heating raises temperatures to millions of degrees. This creates temperature gradients that span 7 orders of magnitude over distances of just a few million light-years. Where are you listening from tonight? As the hours have passed and you've settled deeper into comfort, have you noticed how your body has found its own optimal temperature for rest? The cosmic web, with its delicate balance of heating and cooling processes, reminds us that temperature regulation is a fundamental aspect of all organized systems, from human bodies to the largest structures in the universe. The dark matter filaments of the cosmic web might also serve as waveguides for exotic forms of radiation that we haven't yet learned to detect. Some theories suggest that dark matter particles might emit very low-energy photons when they interact, creating faint radiation that propagates along the filament structures like light traveling through fiber optic cables. If such dark radiation exists, it would create a hidden communication network spanning the entire universe, streams of invisible light carrying information about dark matter interactions from one end of the cosmos to the other. The cosmic web would serve not just as a structural framework for ordinary matter, but as a vast information processing system operating on scales we can barely comprehend. The evolution of the cosmic web over cosmic time reveals the universe's gradual transition from a smooth, nearly uniform state to the complex, structured reality we observe today. The cold filaments we see now are the remnants of the universe's primordial simplicity, preserved and stretched by cosmic expansion into the scaffolding upon which all cosmic structure is built. Chapter 14: Quantum Vacuum and Virtual Particles in Deep Space. Now let's explore perhaps the most fundamental aspect of cosmic cold, the quantum vacuum itself, the supposedly empty space that exists between particles and fields. Even in the coldest, most empty regions of the universe, quantum mechanics tells us that space is never truly empty, but seethes with virtual particles popping in and out of existence. The quantum vacuum represents the lowest energy state that any quantum field can achieve, but remarkably, this lowest energy state is not zero. Even when all real particles have been removed and temperatures approach absolute zero, quantum fields continue to fluctuate due to the fundamental uncertainty principle of quantum mechanics. Picture the vacuum of space as an infinitely restless sea, where pairs of virtual particles, electrons and positrons, photons and their antiparticles, quarks and antiquarks, constantly appear from nothing, exist for incredibly brief moments, and then annihilate back into the void. These quantum fluctuations create what physicists call the zero-point energy of the vacuum. In the coldest regions of space, where real particle densities drop to nearly zero, these quantum vacuum fluctuations become the dominant form of activity. The virtual particles that populate the quantum vacuum carry energy and momentum, creating subtle but measurable effects that influence everything from the behavior of atoms to the expansion of the universe itself. Peaceful pause. One of the most remarkable predictions of quantum field theory is that the quantum vacuum should exhibit a phenomenon called the Casimir effect. When two conducting plates are brought very close together in a vacuum, they exclude certain wavelengths of virtual photons from the space between them, creating a net attractive force as the vacuum fluctuations outside the plates push them together. This effect has been measured in terrestrial laboratories, confirming that the quantum vacuum is indeed filled with real, though virtual, activity. In the vast spaces between galaxies, where matter densities approach the absolute minimum allowed by quantum mechanics, the Casimir effect and related quantum vacuum phenomena might create subtle structuring forces that influence the evolution of cosmic structure on the largest scales. The energy density of quantum vacuum fluctuations is predicted by some theories to be enormous, perhaps the largest energy density in the universe. Yet observations suggest that if such energy exists, it must be almost perfectly cancelled by negative energy contributions, leaving only the tiny cosmological constant that drives the accelerating expansion of space. In regions of space where temperatures approach absolute zero and matter densities drop to their quantum mechanical minimum, the boundary between something and nothing becomes beautifully blurred. The quantum vacuum represents a form of existence that is neither empty nor full, neither hot nor cold in any conventional sense, but rather existing in a state of pure potential. Some theoretical physicists have speculated that consciousness itself might emerge from quantum vacuum fluctuations, that the complex information processing we associate with awareness could be a natural consequence of the infinite activity that occurs even in apparently empty space. If so, then even the coldest, most isolated regions of the universe might harbor forms of experience that we can't yet imagine. The study of quantum vacuum effects in cosmic environments has revealed that space itself possesses properties that can change under extreme conditions. Near black holes, for instance, the intense gravitational fields can amplify quantum vacuum fluctuations to the point where they become real particles, allowing black holes to evaporate through what's known as Hawking radiation. In the coldest regions of the universe, quantum vacuum fluctuations might create their own forms of organization and structure. Some theories suggest that virtual particles could become correlated across vast distances, creating networks of quantum entanglement that span intergalactic space and connect seemingly separate regions of the cosmos. The quantum vacuum also plays a crucial role in fundamental physics through phenomena like spontaneous symmetry breaking, where the apparently symmetric laws of physics manifest in asymmetric ways due to the influence of vacuum fluctuations. The masses of fundamental particles, the strengths of forces, and even the number of spatial dimensions we observe might all be consequences of how quantum fields interact with the underlying vacuum state. As our understanding of quantum vacuum effects has deepened, we've come to realize that the coldest, emptiest regions of space are actually laboratories for studying the most fundamental aspects of reality. In these cosmic deep freezers, where thermal noise is minimized and quantum effects can manifest clearly, we glimpse the underlying quantum nature of space and time themselves. Are you feeling deeply relaxed now, settled into that peaceful state between waking and sleeping? The quantum vacuum reminds us that even in apparent stillness, there's always subtle activity continuing beneath the surface, just as your sleeping brain will continue its essential processes even when conscious awareness fades into dreams. Recent discoveries in quantum field theory suggest that vacuum fluctuations might be responsible for some of the most important features of our universe. The cosmic inflation that occurred in the first moments after the Big Bang might have been driven by quantum vacuum energy, while the dark energy that currently accelerates cosmic expansion might be a manifestation of vacuum fluctuations on cosmological scales. The possibility that our entire universe emerged from quantum vacuum fluctuations, that everything we see and experience might be the result of a particularly large and persistent fluctuation in an underlying quantum foam, represents one of the most profound ideas in modern cosmology. If true, it would mean that existence itself is a consequence of the fundamental restlessness of the quantum vacuum. In this view, the coldest regions of our universe are not empty voids but windows into the creative potential that underlies all of reality. They show us that even nothingness, when examined closely enough, reveals itself to be an infinitely rich and active domain where possibilities become actualities through the mysterious processes of quantum mechanics. Chapter 15. The Future of Cosmic Cold Heat, Death, and Beyond. As we near the end of our journey through the coldest places in the universe, let's look toward the far future and consider what cosmic cold might mean for the ultimate fate of everything we know. The universe's expansion is accelerating, driven by the mysterious dark energy that comprises about 70% of the cosmic energy budget. And this acceleration has profound implications for the future of temperature throughout the cosmos. In the scenario known as the heat death of the universe, cosmic expansion continues indefinitely, carrying galaxies farther and farther apart until each galaxy exists in splendid isolation, surrounded by ever-growing volumes of empty space. As this expansion continues, the cosmic microwave background radiation becomes increasingly redshifted and diluted, causing the background temperature of space itself to drop ever closer to absolute zero. Picture the universe 100 billion years from now. The last stars are dying, their nuclear fuel exhausted after brief, in cosmic terms, lives measured in trillions of years. The cosmos is populated primarily by white dwarfs, neutron stars, and black holes, all slowly cooling as they radiate their stored energy into the expanding void. Galaxies have become dark, cold places where only the faintest sources of heat remain. Gentle pause. In this far future, the cosmic microwave background will have cooled to temperatures measured in microkelvin millionths of a degree above absolute zero. The universe will have become a vast refrigerator, with temperatures so low that even the quantum vacuum fluctuations we discussed earlier become the dominant source of energy in most regions of space. But the story doesn't end with simple cooling. As temperatures drop and the universe expands, fascinating new phenomena emerge. The crystalline white dwarfs we explored earlier will have had trillions of years to perfect their internal structure, becoming cosmic diamonds of unprecedented purity and size. These objects might serve as natural quantum computers, their crystalline lattices storing and processing information in ways we can barely imagine. Even black holes, those seemingly permanent fixtures of the cosmic landscape, will eventually succumb to the universe's cooling trend. Through the slow process of Hawking radiation, they will evaporate over timescales that dwarf the current age of the universe. A black hole with the mass of our Sun would take about 10 to the power of 67 years to evaporate completely, a number so large that it's meaningless in human terms. As black holes evaporate, they become hotter, not colder. Their surface temperature is inversely proportional to their mass. The final moments of a black hole's existence involve temperatures that exceed anything we've discussed tonight, creating brief fireworks of high-energy particles before the black hole vanishes completely. These will be among the last hot events in an increasingly cold universe. But even after the last black holes have evaporated, the universe won't be completely cold and dead. Quantum mechanics ensures that some activity will continue indefinitely. Virtual particle pairs will continue to pop in and out of existence throughout the quantum vacuum, maintaining a baseline level of activity that can never be completely eliminated. In this far future, the concept of temperature itself might become meaningless. With no thermal reservoirs to define heat flow, no dense matter to exhibit thermal motion, and no radiation fields to carry thermal energy, the universe might exist in a state that transcends our current understanding of hot and cold. Some theories suggest that quantum tunneling effects might allow for spontaneous structure formation even in this cold, empty future. Particles might tunnel through energy barriers to create temporary regions of higher organization, brief flickers of complexity in an otherwise maximally disordered cosmos. These quantum fluctuations might even allow for the spontaneous formation of Boltzmann brains, randomly assembled conscious observers that arise by chance from the thermal fluctuations of the vacuum. Where are you listening from as we contemplate these vast futures? What time is it now in your part of the world? As the night has deepened around us and you've settled into ever greater comfort, you've participated in your own small version of cosmic cooling, your body temperature dropping, your metabolism slowing, your mind preparing for the restorative cold of sleep. The far future scenarios we're exploring might seem bleak, but there's also something profoundly peaceful about them. They represent the universe finding its most stable, most restful state, a cosmic version of the deep sleep toward which you're naturally drifting. In the end, all the chaos and violence of stellar explosions, galactic collisions, and black hole formation gives way to perfect tranquility. Some cosmologists have speculated about even more exotic future scenarios. If the fundamental constants of physics slowly change over cosmic time, the far future might see the emergence of new forms of matter and energy that we can't currently imagine. Cold might give way to new types of organization based on principles we haven't yet discovered. The possibility of cosmic phase transitions, sudden changes in the fundamental structure of space and time, opens the door to futures where our current understanding of temperature becomes obsolete. The universe might undergo transitions analogous to water freezing into ice, but involving the basic fabric of reality itself. In some models, the accelerating expansion driven by dark energy might eventually overcome all other forces, tearing apart atoms, nuclei, and even the fabric of spacetime itself in a scenario called the Big Rip. This would represent the ultimate triumph of cosmic cooling. Not just the absence of heat, but the dissolution of the very structures that make temperature meaningful. Yet even in these extreme scenarios, quantum mechanics suggests that new universes might spontaneously nucleate from the quantum vacuum, creating baby cosmos that begin their own cycles of heating, cooling, and evolution. The story of cosmic cold might not be an ending, but rather a transition to new beginnings we can't yet comprehend. The study of these far future scenarios has revealed that cold is not simply the absence of heat, but a fundamental organizing principle of the universe. As systems cool, they often find new forms of order and stability. The crystallization of white dwarfs, the formation of Bose-Einstein condensates, the quantum coherence that emerges at ultra-low temperatures. All of these show us that cold can be creative as well as destructive. In contemplating the universe's cold future, we're reminded that change and stability are both fundamental aspects of cosmic evolution. The hot, chaotic early universe gradually organized itself into the structured cosmos we see today, and this process of cooling and organization will continue far into the future, creating new forms of beauty and complexity that we're only beginning to imagine. Chapter 16: The Philosophical Cold Meaning in the Void. As we approach the end of our cosmic journey, let's reflect on what the coldest places in the universe might teach us about existence, meaning, and our place in the cosmic order. The profound cold we've explored tonight, from the cosmic microwave background to the quantum vacuum, reveals truths that extend far beyond physics and astronomy. There's something deeply moving about the universe's coldest environments. They represent extremes of isolation, stillness, and emptiness that challenge our everyday assumptions about what it means for something to exist. Yet within this apparent nothingness, we've discovered remarkable richness, quantum fluctuations, complex chemistry, exotic states of matter, and processes that connect to the deepest mysteries of consciousness and reality. The cosmic microwave background, that ancient afterglow of creation itself, reminds us that we're all connected to the universe's earliest moments. Every cubic centimeter of space around you right now carries the faint whisper of the Big Bang, cooled by billions of years of expansion but still present, still carrying information about our cosmic origins. In the Boomerang Nebula's record-breaking cold, we see beauty in endings, a dying star creating something unprecedented through the simple act of letting go. There's a lesson here about finding meaning and purpose even in apparent dissolution, about how the process of cooling and releasing can create new forms of wonder. Peaceful pause. The brown dwarfs wandering through space teach us about persistence and patience. These failed stars will continue to shine, however dimly, long after our sun has died and been forgotten. They represent a kind of cosmic endurance, finding ways to maintain their existence even without the nuclear fires that define true stars. The quantum vacuum shows us that emptiness is never truly empty, that even in the coldest, most isolated regions of space, subtle activity continues. This suggests that existence might be more fundamental than we imagine, not something that emerges from nothingness, but something that can never be completely eliminated. The rogue planets drifting between stars embody a kind of cosmic courage, worlds that have found their own path through the universe, discovering new forms of stability and perhaps even life in environments that seem impossibly hostile. They remind us that survival and even flourishing might be possible under conditions far more extreme than we usually consider. The intergalactic voids, those vast empty spaces between galaxy clusters, teach us about scale and perspective. They show us that most of the universe consists of profound emptiness, yet this emptiness is structured, meaningful, and connected to the cosmic web that gives rise to all the complexity we observe. As you lie here now, preparing for sleep, you're participating in your own version of cosmic cooling. Your body is finding its optimal temperature for rest. Your brain is shifting into the slower rhythms that characterize deep sleep. Your entire being is transitioning toward a more peaceful, more ordered state. There's something profoundly comforting about recognizing our connection to these cosmic processes. The same physical laws that govern the cooling of white dwarfs and the formation of molecular clouds also govern the biochemistry that allows you to rest and restore yourself each night. You're not separate from the cosmos, you're an expression of it, a way the universe has found to experience and understand itself. The coldest places in the universe might seem hostile to life as we know it, but they're also the laboratories where the universe explores its most fundamental possibilities. In the profound stillness of these environments, matter finds forms of organization and behavior that reveal the deep quantum nature of reality itself. Perhaps most importantly, These cold cosmic environments remind us that rest and stillness are not signs of death or failure, but natural and necessary aspects of existence. Just as your body needs sleep to maintain its health and function, the universe needs its cold, quiet regions to maintain the delicate balances that allow for complexity and life. Where are you listening from tonight? What time has it become as we've journeyed together through these frozen realms? Whether you're in a bustling city or a quiet countryside, in the depths of winter or the warmth of summer, you're surrounded by connections to the cosmic cold we've explored. The quantum vacuum that underlies all space, the cosmic microwave background that bathes everything in ancient light, the ongoing expansion that carries galaxies ever farther apart. The study of cosmic cold has revealed that the universe is far stranger, far more beautiful, and far more interconnected than our everyday experience suggests. The temperature contrasts we've explored, from the blazing cores of neutron stars to the profound chill of intergalactic space, show us a cosmos of incredible diversity and complexity. But perhaps the most important lesson from our journey is that extremes often reveal truths that more moderate environments hide. In the coldest places in the universe, we discover quantum mechanics, exotic matter states, and forms of organization that challenge our basic assumptions about the nature of reality. These extreme environments serve as windows into the fundamental structure of existence itself. As you prepare to transition into sleep, carry with you the sense of wonder and peace that comes from contemplating these cosmic extremes. You're part of a universe that contains infinite variety, from the hottest stellar cores to the coldest quantum laboratories, from the densest matter to the emptiest voids, from the chaos of galactic collisions to the perfect order of crystalline white dwarfs. Chapter 17: The Science of Sleep and Cosmic Cold. Before we conclude our journey, let's explore the beautiful parallels between your body's natural cooling process as you prepare for sleep and the cosmic cooling processes we've discovered throughout the universe. Sleep, like cosmic evolution, is fundamentally about temperature regulation, energy conservation, and the transition from active, chaotic states to more ordered, restful ones. As you've been listening tonight, your body has been naturally cooling itself in preparation for sleep. Your core body temperature typically drops by about 1 to 2 degrees Celsius as you transition from wakefulness to slumber, a small change that reflects the same physical principles governing the cooling of stars, planets, and the universe itself. This temperature drop isn't accidental. It's a carefully orchestrated process that involves your brain's hypothalamus acting as a biological thermostat. Just as the universe finds stability through cooling and expansion, your body finds the restorative state of sleep through its own controlled cooling process. The cooling that occurs during sleep serves many of the same functions as cosmic cooling. Lower temperatures allow for more efficient energy storage, reduced metabolic activity, and the emergence of organized patterns that would be disrupted by thermal chaos. Your sleeping brain exhibits synchronized neural oscillations, waves of electrical activity that sweep across your cortex in coordinated patterns, much like the organized structures that emerge in matter as it approaches absolute zero. Gentle pause. Just as quantum coherence becomes possible in ultra-cold environments, your sleeping brain achieves forms of coherent activity that are impossible during the thermal chaos of waking consciousness. The slow waves of deep sleep represent a kind of neural Bose-Einstein condensate, where individual neurons surrender their independent activity to participate in larger, more unified patterns of brain function. The cosmic microwave background that we explored earlier has its parallel in the baseline electrical activity of your sleeping brain. Even in the deepest stages of sleep, your neurons maintain a kind of background firing rate, a neural equivalent of the universe's thermal afterglow, quietly persisting even when more dramatic forms of activity have ceased. The molecular clouds where stars are born share similarities with the neurochemical processes that occur during sleep. Just as these cosmic nurseries use profound cold to preserve and organize the raw materials for stellar formation, your sleeping brain uses lowered temperatures and altered chemistry to consolidate memories, clear metabolic waste, and prepare for the next day's activities. The brown dwarfs we discussed, those objects that glow dimly with their own internal heat, resemble your sleeping body, which continues to generate and radiate warmth even in its most restful state. Both represent systems that have found sustainable, long-term ways to maintain their essential functions while operating at reduced energy levels. The quantum vacuum fluctuations that persist even in the coldest regions of space mirror the subtle activity that continues in your sleeping brain. Even during the deepest stages of sleep, your neurons maintain the quantum-level processes that sustain consciousness, just as the vacuum maintains its fundamental activity even at absolute zero. Are you feeling the natural drowsiness that comes as your body temperature drops and your brain begins its transition towards sleep? This is your personal participation in the same physical processes that govern cooling throughout the cosmos, the natural tendency of all systems to find their most stable, most energy-efficient states. The intergalactic voids we explored, with their profound emptiness punctuated by subtle structure, resemble the mental state that emerges as you drift towards sleep. Conscious thoughts become more sparse and disconnected, while deeper, more fundamental processes continue to operate beneath the surface of awareness. The rogue planets wandering through interstellar space share something with your dreaming mind. Both represent systems that have found ways to maintain complex internal activity, even when disconnected from their usual energy sources. Dreams, like rogue planets, create their own internal weather systems, their own landscapes of experience independent of external input. The crystallization process occurring in cooling white dwarfs parallels the memory consolidation that takes place during sleep. Just as carbon atoms arrange themselves into perfect crystalline structures as white dwarfs cool, your experiences from the day arrange themselves into lasting memory structures as your brain cools and transitions through different sleep stages. The cosmic web of dark matter filaments that connect galaxies across vast distances resembles the neural networks that remain active during sleep, maintaining the connections between different brain regions while allowing for the synchronized activity that characterizes healthy sleep patterns. What time is it now where you are? Has your body found that perfect temperature for sleep? Not too warm, not too cold, but just right for the deep rest that awaits? You've been naturally participating in your own version of cosmic evolution, allowing thermal equilibrium and reduced activity to guide you toward the restoration that sleep provides. The future cooling of the universe that we contemplated, that far future when all stars have died and only the faintest heat sources remain, shares something with the profound rest that comes in the deepest stages of sleep. Both represent states where activity is minimized but not eliminated, where subtle processes continue while more dramatic forms of energy expenditure cease. Even the quantum tunneling effects that might occur in the far future of the universe have their parallel in sleep, where thoughts and memories can make unexpected connections, tunneling through the usual barriers of logical association to create the strange, beautiful narratives we call dreams. Chapter 18: The Warmth of Connection in Cosmic Cold. As we near the end of our journey through the universe's coldest environments, let's reflect on a beautiful paradox. Even in the most isolated, frigid regions of space, we find evidence of connection, relationship, and interaction. The profound cold we've explored reveals not emptiness, but a deeper form of unity that underlies all existence. The cosmic microwave background, stretched and cooled by billions of years of expansion, still carries information about the universe's earliest moments when all matter and energy existed in perfect thermal equilibrium. This ancient radiation connects every point in space to every other point, creating a web of shared history that spans the observable universe. In the quantum vacuum, virtual particle pairs pop into existence and immediately annihilate, but in their brief existence, They maintain quantum correlations that Einstein called spooky action at a distance. Even in the emptiest regions of space, these quantum connections persist, linking distant regions through entanglement relationships that transcend our ordinary understanding of separation and isolation. The cosmic web of dark matter filaments that we explored creates a hidden network connecting all the galaxies we can see. Matter flows along these invisible highways, carrying chemical elements forged in stellar cores to distant regions where they can participate in new cycles of star and planet formation. Even the coldest regions of space participate in this grand recycling project. Peaceful pause. The brown dwarfs drifting through space, cooling slowly over billions of years, still maintain gravitational relationships with the galaxy as a whole. They orbit the galactic center in stately trajectories that connect them to the same dynamic system that includes our own solar system. Their isolation is only apparent. They remain part of the larger gravitational symphony that governs galactic structure. The rogue planets we discussed, ejected from their birth systems and wandering alone through interstellar space, carry with them the chemical signatures of their origins. They're living libraries of stellar nucleosynthesis, preserving information about the specific conditions that existed in their birth systems billions of years ago. Through these wandering worlds, the history of stellar evolution is distributed throughout the galaxy. Even the intergalactic voids, those vast empty regions between galaxy clusters, are threaded with the subtle influence of dark energy, the mysterious force that drives cosmic acceleration. This invisible energy field connects every point in space, creating a uniform influence that shapes the evolution of the universe on the largest scales. The neutron stars we explored, with their extreme temperature gradients, demonstrate how cosmic objects can maintain both hot and cold regions simultaneously. They show us that temperature is not a uniform property, but a complex landscape that can vary dramatically over small distances, creating opportunities for diverse physical processes to coexist within single objects. The molecular clouds where stars are born illustrate how the coldest regions of space can serve as nurseries for the hottest objects. The profound chill that allows chemical complexity to develop eventually gives birth to nuclear furnaces that will burn for billions of years. Cold and heat are not opposites but partners in the cosmic dance of creation. As you lie here now, feeling your body's natural warmth even as your temperature drops towards sleep, you're experiencing your own version of this cosmic paradox. Your cooling body maintains perfect thermal regulation, ensuring that the chemical processes essential for life continue even as you transition toward rest. The quantum effects we've discussed throughout our journey, from the behavior of matter at absolute zero to the fluctuations of the vacuum itself, reveal that separation and connection are more subtle concepts than our everyday experience suggests. At the deepest level, all matter and energy participate in the same quantum fields that fill all of space. The study of cosmic cold has shown us that the universe is not a collection of isolated objects scattered through empty space, but a unified system where every component influences every other component through a network of physical relationships. Gravity, electromagnetism, the strong and weak nuclear forces, all of these create connections that transcend the apparent boundaries between objects. Where are you as you listen to this reflection on cosmic connection? Whether you're alone or with others, in a city or in the countryside, you're participating in relationships that extend from the quantum level to the cosmic scale. The atoms in your body were forged in stellar cores. The energy powering your thoughts comes from nuclear reactions in the sun, and the very expansion of space affects the fundamental constants that make your existence possible. The coldest places in the universe teach us that stillness and activity, isolation and connection, emptiness and fullness are not absolute categories but different aspects of a more complex reality. In the profound quiet of intergalactic space, quantum fluctuations maintain the underlying activity that prevents true nothingness. In the isolation of rogue planets, gravitational relationships persist across vast distances. Perhaps most beautifully, the cooling processes we've explored throughout our journey all share a common tendency toward greater order and organization. Whether we're looking at the crystallization of white dwarfs, the formation of molecular clouds, or the emergence of quantum coherence in ultra-cold gases, cooling generally leads not to chaos but to new forms of structure and beauty. This suggests that the universe's overall cooling from the hot, dense state following the Big Bang to the cold, expanded cosmos we observe today is not a story of decay and death, but of increasing organization and complexity. The cooling that allows atoms to form, molecules to assemble, stars to ignite, and life to emerge is the same cooling that will eventually lead to forms of organization we can't yet imagine. As you prepare for the restorative cooling of sleep, you're participating in this cosmic tendency toward beneficial organization. Sleep doesn't represent a shutdown of your body's systems, but a reorganization that allows for healing, memory consolidation, and preparation for tomorrow's activities. Chapter 19. The Poetry of Absolute Zero. In these final moments of our cosmic journey, let's appreciate the profound poetry that emerges from the universe's coldest environments. There's something deeply moving about absolute zero, that theoretical temperature where all thermal motion ceases, where atoms find perfect stillness, where the chaotic dance of particles finally comes to rest. Absolute zero represents more than just a temperature. It's a concept that touches on the deepest philosophical questions about existence, motion, and the nature of reality itself. At absolute zero, the boundary between being and non-being becomes beautifully ambiguous. Matter still exists, but in a state so quiet, so still, that it approaches the realm of pure possibility. The journey toward absolute zero is asymptotic, can be approached but never reached. This mathematical property mirrors many aspects of human experience. The approach toward perfect understanding, perfect peace, perfect love. We can always get closer, but the final step remains forever elusive, forever mysterious. In the laboratory-created ultra-cold gases that approach absolute zero, we witness matter undergoing a kind of spiritual transformation. Individual atoms lose their separate identities and merge into collective quantum states, Bose-Einstein condensates where thousands of particles behave as a single entity. It's as if matter learns to meditate, transcending individuality to participate in a larger unity. Gentle pause. The cosmic approach toward absolute zero occurs on timescales that dwarf human imagination. The universe began at infinite temperature, or at least temperature so high that our physics breaks down, and has been cooling ever since. We're living in a brief, warm moment in cosmic history, a fleeting epoch when stars can shine and life can flourish before the final cooling reduces everything to perfect stillness. But even in this far future, when the cosmic microwave background has cooled to nanokelvin temperatures and the last black holes have evaporated away, quantum mechanics ensures that perfect stillness remains impossible. The uncertainty principle forbids absolute rest, maintaining a minimal level of activity that prevents the universe from achieving true nothingness. This suggests that existence itself is built into the fundamental structure of reality. Even at absolute zero, even in perfect vacuum, even in the most profound cosmic winter, something persists. The universe cannot achieve true nothingness because nothingness itself is unstable, constantly giving birth to virtual particles and quantum fluctuations. The poetry of cosmic cold lies partly in its revelations about time. In the coldest environments, processes that would occur instantly at higher temperatures can take millions or billions of years. Chemical reactions proceed through quantum tunneling at rates so slow they challenge our patience. Stellar cooling occurs over timescales that span the entire future history of the universe. This extreme slowing of time in cold environments creates a kind of cosmic meditation, where processes that are usually too fast to observe can be watched unfolding over geological epochs. the cooling of white dwarfs, the evaporation of black holes, the crystallization of neutron star matter. All of these represent the universe taking its time, proceeding with infinite patience toward its ultimate destinations. The coldest places in the universe also reveal the deep democracy of physical law. The same quantum mechanics that governs atomic behavior in terrestrial laboratories also determines the properties of matter in the cosmic microwave background. The same thermodynamics that describes your body's cooling as you fall asleep also governs the evolution of stars and galaxies. This universality of physical law creates a profound connection between your immediate experience and the most exotic cosmic environments. The drowsiness you're feeling right now, the gradual slowing of your thoughts, the peaceful transition towards sleep, all of this participates in the same fundamental processes that govern cooling throughout the universe. Are you feeling that gentle tiredness now, that natural settling toward rest that comes as night deepens? Your body's wisdom in seeking the optimal temperature for sleep connects you to the cosmic wisdom that guides all systems toward their most stable, most restful states. The approach toward absolute zero also reveals the beautiful relationship between energy and information. As systems cool and thermal noise decreases, subtler forms of organization become possible. Information can be stored and processed more reliably, quantum coherence can be maintained over larger scales, and complex correlations can persist without being disrupted by thermal chaos. In the coldest cosmic environments, the universe might be engaging in forms of information processing that we can barely imagine. The quantum correlations that persist in ultracold gases, the crystalline order that emerges in cooling white dwarfs, the synchronized oscillations that might occur in dark matter filaments, all of these suggest that cooling enables new forms of cosmic computation and organization. Perhaps consciousness itself is favored by cooling environments. The neural oscillations that characterize your sleeping brain require the reduced thermal noise that comes with lower temperatures. The quantum processes that some theories suggest might be crucial for consciousness become more robust as temperatures drop and quantum decoherence is minimized. If so, then the universe's long-term cooling might not represent the death of consciousness but its transformation into new forms adapted to ultra-cold environments. The cosmic winter that awaits might be not an ending but a transition to modes of awareness and experience that we can't currently comprehend. What time is it now where you are listening? How has your sense of temperature and comfort evolved as we've journeyed together through these cosmic extremes? You've spent these hours participating in your own approach toward the restorative cooling of sleep, allowing your body's natural wisdom to guide you toward the rest you need. The poetry of absolute zero ultimately reminds us that rest is not the opposite of activity but its deepest foundation. In the stillness that approaches absolute zero, we find not emptiness but the quiet substrate from which all activity emerges. The cosmic cooling that defines the universe's evolution creates the conditions that allow for stars, planets, life, and consciousness to flourish in their brief, warm moments. Chapter 20. The Gentle Conclusion: Finding Rest in Cosmic Perspective. As our journey through the coldest places in the universe draws to a close, let's rest together in the profound peace that comes from cosmic perspective. We've traveled from the quantum vacuum to intergalactic voids, from laboratory-created ultra-cold gases to the far future of cosmic evolution, discovering that cold is not empty but full, not lifeless but creative, not isolated but connected. The universe we've explored tonight is vast beyond imagination, containing temperature extremes that span more than 100 orders of magnitude. Yet within this immensity, we've found patterns and processes that mirror your own experience. The natural cooling that prepares you for sleep, the transition from chaos to order, the deep rest that enables renewal and growth. Every breath you take connects you to the cosmic microwave background that fills all of space. Every quantum process in your brain participates in the same fundamental fields that govern matter in the coldest environments we've discovered. You are not separate from these cosmic wonders. You are an expression of them, a way the universe has found to experience and understand its own magnificent complexity. Long, peaceful pause. The brown dwarfs cooling slowly over billions of years, the rogue planets wandering through interstellar space, the crystalline white dwarfs that will outlast nearly everything else in the cosmos. All of these teach us about patience, endurance, and the deep wisdom of finding sustainable ways to exist. They show us that there are many ways to shine, many ways to persist, many ways to contribute to the cosmic story. The molecular clouds where stars are born demonstrate that the coldest environments can serve as nurseries for the most spectacular creations. The quantum effects that emerge at ultra-low temperatures reveal new forms of order and organization that transcend our ordinary understanding of matter and energy. Even the emptiest regions of space pulse with virtual particles and quantum fluctuations that prevent true nothingness from ever emerging. These discoveries remind us that apparent opposites, hot and cold, empty and full, chaos and order, activity and rest, are not contradictory but complementary aspects of a deeper reality. The universe needs its cold, quiet regions just as much as it needs its hot, active ones. Both play essential roles in the cosmic dance that gives rise to complexity, beauty, and consciousness. As you settle into sleep tonight, you participate in this same complementary relationship. Your active, thinking, experiencing consciousness gives way to the restorative processes of sleep. Not as an ending but as a different form of activity, one that's essential for maintaining the complex organization that makes conscious experience possible. Where are you now as we conclude this cosmic meditation? Have you found that perfect position, that ideal temperature, that peaceful state of mind that allows for deep rest? Your body's wisdom in seeking these optimal conditions connects you to the same principles that govern the cooling and organization of matter throughout the universe. The coldest places in the universe are also, paradoxically, some of the most revealing. In their profound stillness, they expose the quantum nature of reality, the deep connections that link all things, and the creative potential that emerges when thermal chaos gives way to organized tranquility. They show us that rest is not the absence of meaning but its deepest source. The journey toward absolute zero that we've explored, whether in cosmic environments or terrestrial laboratories, represents more than just temperature reduction. It's a journey toward fundamental truth, toward the basic principles that govern existence itself. In the coldest environments, matter reveals its quantum nature, space reveals its geometric structure, and time reveals its relationship to energy and information. Your own journey towards sleep tonight parallels these cosmic processes. As your body temperature drops and your brain activity shifts into the slower rhythms of rest, you approach your own biological equivalent of absolute zero, not the cessation of life, but its deepest restoration. Sleep is your daily return to the fundamental state that enables all your waking activities. The universe we've explored together is both unimaginably vast and intimately personal. The same laws that govern the cooling of neutron stars also govern the biochemistry that allows you to rest. The same quantum mechanics that creates exotic matter states in cosmic environments also enables the neural processes underlying consciousness and dreams. In this recognition of deep connection, we find not diminishment of human significance but its ultimate foundation. You are not a random accident in an indifferent cosmos, but an integral expression of the universe's own capacity for awareness, understanding, and appreciation of beauty. The coldest places in space reveal the same fundamental creativity that gave rise to your ability to contemplate them. Final gentle pause. As you drift towards sleep now, carry with you the sense of wonder and peace that comes from recognizing your place in the cosmic story. You are made of elements forged in stellar cores, organized by processes that span from quantum mechanics to cosmic evolution, participating in the same dance of cooling and warming, activity and rest. that characterizes the universe as a whole. The profound cold we've explored together reveals not emptiness but fullness, not isolation but connection, not ending but transformation. In the universe's coldest environments, we discover the patient creativity that underlies all existence. The same creativity that allows you to rest, restore, and awaken each day renewed and ready to participate once again in the magnificent complexity of conscious existence. Sleep well, fellow traveler of the cosmos. Dream of quantum crystals and rogue planets, of cosmic voids and molecular clouds, of the profound peace that emerges when all systems find their most natural, most restful states. In your sleep, you join the universe in its eternal practice of cooling, resting, and preparing for new cycles of activity and creation. The coldest places in the universe are ultimately about coming home, to rest, to peace, to the fundamental ground of being from which all complexity emerges and to which it all returns. Tonight, you come home to sleep, participating in the same cosmic rhythm that governs everything from quantum vacuum fluctuations to the evolution of galaxy clusters. Rest well in this knowledge. Rest well in this connection. Rest well in the gentle cooling that carries you toward the restorative darkness of sleep, where your dreams will weave together the cosmic wonders we've explored into new patterns of meaning and beauty. Welcome to the peaceful cold of sleep, where your consciousness finds its own version of absolute zero, not the end of experience, but its deepest renewal. Good night, and sweet dreams of the infinite cosmos that cradles us all.